Hello all, welcome to the deep learning series. So in this video, we are going to see about the introduction to deep learning. And these are going to be the key takeaways of this video. So we're going to see what is deep learning and the difference between machine learning and deep learning. What are the building blocks of deep learning? So they're going to be perceptrons and activation function. And finally, we will see how we can build a neural network using perceptron. Okay, so before getting into the details of deep learning, we'll understand the connect between the human brain and the neural network. So inside our human brain, we all know that we have nerve cells, which is called neurons. So you see the neuron picture here. And here we see the artificial neural network, a simple picture of that. So there's a lot of connect between because like the artificial neural network is inspired from the biological neural network that we have. So while we do any task, so be it doing any work or like predicting, so let's say you're predicting the voice of a person whom you're listening to after so many years, or taking a decision whether to listen to a music or taking up your assignment. So whatever it is, whenever you do such things, your neurons are communicating with each other and your sensory organs, and the task is being performed. So inspired by this architecture, so the artificial neural network also has neurons in them. So this you see as a neuron. So this we call it as a perceptron. So this perceptron, like neurons, the biological neurons, these artificial neurons get signals from the input data. So the input data can be a text data, can be an image, it can be a video. And this input is not input as such. The features of the data are fed as the signals to the perceptron of the neuron, and a mathematical calculations are applied here, and an output is squeezed out. So based upon this output, a prediction task is performed, or a classification, or a recognition. So you can do speech recognition, or you can classify whether it is a dog or a dog image or a cat image or whatever. So the basic thing was inspired from the biological neuron. So these are the applications of deep learning. So there can be many other deep learning which are not covered in this slide. But to have a gist of that, so we have image recognition. So you can do a face recognition. You can recognize a person or an animal or whatever. And natural language processing, you can process text or speech. You can do a speech recognition. You can do text classification, sentiment analysis, and you can do predictions of stock, drug discovery, diagnosis of diseases, and breast cancer, for instance, speech recognition, and you have self-driving cars also. So there are a number of deep applications that come under the deep learning paradigm. Okay, so we've been using the both the terms deep learning and neural networks. The deep learning is nothing but like when you train a neural network, the artificial neural network, to perform any task. So that is called as deep learning. Okay, so coming to the difference between machine learning and deep learning. So there's only one difference we can see here. Like when you look at the deep learning paradigm, so it is you have the data here and you have a black box in between, and the output is obtained. So when you look at the machine learning thing, so you have the data and you do the manual feature extraction, and you apply the algorithm, and you get the output. So this feature extraction, for instance, like you are classifying the image, so or classifying the animals as in this picture shows. So you give a bunch of animal pictures and you're classifying them with their names, so penguins or dogs or cats or whatsoever. So in this case, then you have to specify the features. Like if you have a text, then you have to specify the features, hand code the features. You need expertise. So whereas in deep learning, so it's the other way around. It's an end-to-end. You can build end-to-end models. You just need to feed the data, and the network takes care of understanding the patterns or the features on its own, and the job is done. So this is what is the difference between machine learning and deep learning. Okay. So now coming to the part of like how deep learning actually understands or extracts the features from the underlying data, so that are underlying within the data. So for instance, so we see here, we see an image here. So this is for a face recognition task. So let's say we are given a bunch of images and we are supposed to build a face recognition system. Then how does the deep learning algorithm understands or extracts the features out of the images given to it? So first, it does in a hierarchical manner. So it starts from the low level features. Maybe it understands the lines and edges of the face, and then it just travels up to understand the nose and the eyes and ears, and finally to the deep level features. So that is facial structures. This is in terms of this is in the case of image. So when you are processing text, then you may be like starting with the words and their word meanings, embeddings, and then you try to understand the a sentence level and the paragraph level features, and that's how deep learning algorithms understand the features or extracts the features. Okay, so now if you're comfortable with the term deep learning, we'll understand how it actually works. So in this picture, you see a simple a single perceptron model. We'll understand in parts. So we'll understand, we'll start from here. So this is called the input layer, and this is the output layer. And in between output and input, you see a summation function and you see an activation function. So we'll see one by one. We'll start from the input. So you see a 1 here. So this 1 is not part of the input, and this is a bias. So I'll come to that shortly. So we'll just finish the inputs. So these are the inputs. These are not x1, x2, xm are inputs. They're not the data, but they are the features representing the data. Okay, so now each feature is associated with a weight. So not all features are important to do the classification task or any task we are destined for. So we have an output, so we have a task in front of us. So for instance, let's say we are doing a classification of an image. So let's say we are doing a classifying a dog image. We are distinguishing between a dog and a cat. To distinguish that, like not all the features of the images are very important to us. So only part of the images are the part of the image is very important to us. So those features are given high weightage, and the rest of the features are given the less weightage. So that's what this weight um, means to these features. So these weights are nothing but how much influence that particular feature is having towards doing this particular task. That's what weights mean. Okay, so now this bias is not part of the image. So we just introduce bias into the network wantedly to introduce some flexibility to the model. So let's understand bias. So it is something like our mx plus c equation, that is straight line equation. This is intercept, right? Like it's similar to that. For instance, you have a straight line. So we can control this straight line. So let's say this straight line is doing some classification job or a regression task. So this straight line can be controlled by controlling this intercept. So this intercept tells us like where this line is cutting the y-axis. So similar, we can move up and down by controlling over this intercept. So similarly, so we can have a control over this network to an extent through this bias. They're not part of the input, and here we have only one layer in between the input and output. We can have n number of layers in a neural network. How much ever layer we have, these bias terms, these bias neurons. So these are neurons actually. So they are added to the each and every layer, and they don't communicate between the layers. That means like they don't pass information like the rest of the neurons do between the layers. So they are just wantedly introduced into the each layer for introducing some flexibility to the network. So that's the story of the bias. And coming to the summation, what the summation do is that it takes all the inputs, including the bias, multiply them with their respective weights, and then sum them up. That's what we see here. So this is the weight of the bias. So since it is 1, so it's W naught. So plus, and we are adding the bias, and we are summing all the weights multiplied with their features. So m is the size of the input that we have. Okay, so now this is a linear function that we see. Okay, so and then we are passing to a nonlinear function. That nonlinear function is nothing but this activation function. Okay, so then what is the necessity of having a nonlinear function? So when we have a linear combination of inputs, we'll understand that shortly. So the output of the activation function is only given as the input, given to the, I'm sorry, given to the output. So we have input, and we take all the inputs multiplied by their weight, add the bias, and then pass it on to the activation function, and then squeeze it to the output to do a particular task. So be it a regression task or a classification or prediction task. So this X is you can do you can think of a matrix. Yeah, it is a matrix. So matrix of features, and weight is the matrix of the weights of the features themselves. Okay, so still we've not understood like what is the necessity of the activation function. So we'll see an example. We are given the weights of the features. Let's say we have only two inputs and their weights, and this is the weight of the bias term. So when we do the summation and by multiplying with the weights, so we get this linear combination of the inputs. It's actually a line in two dimension. So now, so we have to pass this line into an activation function, but what is the need for that? We'll understand. So ultimately, it is a line. So what we have is a line in front of us, but can we do a classification or a prediction using that line is the question. Okay, so now let's say this is the task given to us to distinguish between to classify between the red dots and the green dots. If we have a line with us, like we can't put a line and classify them, and the task won't be complete. So here, what we need is not a line. We need a curve. So something like this. In this picture, you have a curve, right? So a non-linear curve which is actually distinguishing the green dots and the red dots. So this non-linearity is actually introduced by the activation function. So that's why we pass on the input and the multiplying the inputs, and we did a summation, right? We got a linear combination of the inputs. So that we are passing to an activation function to introduce nonlinearity into the neural network. So that is the reason why we why we need an activation function. So we'll understand them a bit more. So we have many activation functions. So sigmoid is a very old one. So you'll understand how that non-linearity happens. So we have a linear a function with us. So after we get the inputs and we multiply the weights and we add them, we have a linear combination of inputs. So what happens to them? Like we actually pass on to the activation function. So the sigmoid function is actually this is the sigmoid function. So 1 by 1 plus e to the power of minus x. So this x is the value that you give. So any value that you give, sigmoid function gives you a value between 0 to 1. So that's what it gives. Whatever you pass on to the sigmoid function, that's what it gives. So you understand that. So this is the sigmoid function actually. Whatever you give value of x, it gives 1 by 1 plus 1 by 1 plus to e to the power of minus 6. That's what the job of a sigmoid function. We'll understand first this graph. So you see a graph of e to the power of minus x. Okay. So what happens to e to the power of minus x every with the various values of x? When the x is going to the large negative sides, so reaching the large negative values. So this e to the power of minus x is tending upwards to plus infinity. Okay, so whenever the x is having a large negative values, it is the e power minus x is going in the positive direction in the infinite by infinite values. So its value is getting large in the positive side. Then what happens when x is 0? So when x is 0, this e to the power of when x is 0, this e to the power of minus x is 1. And when the x is going in the positive direction, it's getting large in the positive direction, what happens? This e to the power of minus x gets saturated and it reaches the value of 0. So that is the story of e to the power of minus x. So but our sigmoid function is 1 by 1 plus e to the power of minus x. So that's what happens. So whenever you have x as large negative values, your sigmoid function will always give 0. So 1 by 1 plus infinity. So because like when x was minus infinity, so e to the power of minus x was plus infinity. So 1 by 1 plus e to the power of I'm sorry, 1 by 1 plus infinity is 0. Likewise, when x was 0, so the e to the power of minus x was 1. So obviously 1 by 2 is 0.5. So similarly, when x is large in the positive side, so when it is reaching higher positive values, then the sigmoid function is going to be 1. So this sigmoid function will look like a S-shaped curve. So it is always between 0 to, this graph is very poorly drawn, pardon. So it ranges from 0 to 1. So the moral of the story is it ranges from 0 to 1. And so the classification is done by having zero point 0.5 as the center. Like any values that are crossing zero point 0.5 is one class, and above zero point 0.5 is one class, and below zero point 0.5 is another class. That's how the classification task is done using the sigmoid function. Okay, so now we will understand. Yeah, this is an example. So you have this linear combination of input. So the actual value when you pass on to the sigmoid function is 0.002. So that's how what we are actually doing is that, like, no matter what values we have, so actually we are given the values for x here. So you have x as minus 1, 2. When you plug this minus 1, 2 is the input value that you get. When we plug this input into this equation, so we get minus 6. That minus 6 is passed on to the passed into the activation function. This is sigmoid activation function, which is giving the value 0.002. So it is squeezing the values between 0 to 1. So that's what activation function does. So this introduces some nonlinearity, so which will help us to do our classification of prediction task better. And yeah, so yeah, so as I said, like, this is how the sigmoid graph will look like. So it is centered towards 0.5, and it is always the values are always between 0 and 1. Like sigmoid, there are many other activation function, hyperbolic tangent and ReLU, rectify linear unit. So this is widely used. And sigmoid, when we talk about sigmoid function, it is the oldest one, but it is not widely used in practice. But its generalized version, that is softmax, it is used in the output layer while we do a classification or a prediction task. And hyperbolic tangent, when sigmoid function can squeeze between 0 and 1, hyperbolic tangent can squeeze the values between 0 to 0, minus 1, I'm sorry, minus 1 to plus 1. So centered to 0. So that is the nature of hyperbolic tangent. So they're all mathematical functions. So but both sigmoid function and hyperbolic tangent function, they suffer with the vanishing gradient. So we'll understand vanishing gradient later in the upcoming videos when we learn about backpropagation. But when we talk about gradient, so without activation function, we'll understand this better, like when we come up about when we learn about backpropagation. But apart from introducing nonlinearity, uh, without this activation function, taking a partial derivative. So when we train the network, so that is not possible. These activation functions are not present. So in the neural network. So as of now, we can just have this in mind. Maybe when we catch up with backpropagation, we'll understand even more, even better. Yes, okay. So ReLU is most opted. It does not suffer much by vanishing gradient like hyperbolic or sigmoid, but ReLU is mostly opted in the hidden layers. So it's not opted in the output layer. So it's mostly opted in the hidden layers as the activation function. What we have seen for seen so far is the single perceptron model. So like we had a single perceptron collecting inputs from the data, so we can also have a stack of perceptron like we see here. So this forms the hidden layer, and we already saw this as to be a input layer, and this is the output layer. So when this happens, like what happens to the equation, we'll see. So this number represents the layer in which the weights are representing. This is a weight matrix representing the weights of the first layer, that is input layer. So this weight matrix is representing the weights of the second layer. So yeah, so we'll understand this. So we have the I, right? So Z1. So let's say this is Z1. Let's just focus on this. The Z1 will be the bias term added to it. So it's not shown here. So you'll have one bias term plus you have the summation of the x1 and x2, x3, all the features and their associated weights connecting to Z1. So all these. So all these three, so they are multiplied and they are summed up. That's what the Z1 will have. Similarly, Z2 will have the features multiplied with the weights associated to it with the respective. So it's not necessary. The moral of the story is that like not all the features are associated to each of the activation these neurons with the same weights. They can have varying weights associated with them, so they are finally summed up. So now this each Z will be passed on to an activation function. That's what is the output emitted by this particular neuron, that is G of Z1, and that is multiplied with another weight matrix represented by W2. So that's what we see here. So when that is going to the output layer, we see here what we see here is that, for instance, here Z1 will be the G of Z1 will be multiplied by, like we multiplied with X1 and its weight. Now we are multiplying with a G of Z1. That is the activation output multiplied with the respective weight tied to the output layer with Z1, and we are multiplying it, and we are also summing it up with the rest of the neurons and their associated weights tied to the output layer. So that's how we get it, and then we pass on again. We need an activation function. You see this G, and then we get the final output. So that is how the final output is obtained. So like we did for a single neuron, single perceptron. So we get single neuron or perceptron. We can also do it for a stack of a perceptron, and we can do the task. Like we have single hidden layer, we can also have multiple hidden layers communicating with each of them, and they can do the job as we did here. Okay, so so far what we have seen is that forward propagation. So that is when you give an input, you give some weights associated with that, and then you have some activation function, and you multiply the weights, sum them up, pass it on to the activation function, and then you squeeze it to the output. That's what we have seen. So this is one part of the story, that is forward propagation. So when we do this, there's no guarantee that like there's only one pass. That is, you start from the input and you arrive at an output. There is no guarantee that the neural network will do its job correctly. to do its job correctly, we have these weights, right? So these weights has to be there's no guarantee that these weights are always right in the first pass. So we need to align these weights. So we said this neural network is a black box, right? Like we have certain controls. This weight is one of the controls. So we cannot change the input. What we can change is the weight matrix. So initially we can have some weights. We may go wrong. Later, what we can do is that depending upon the error that we get from the network, we can change this weights, updates this weight, and we can keep repeating this until we actually arrive closer to the actual output. So that is what is called backward propagation. So about which we will see in the next video. So in this video, what we have seen so far is that we now know what is deep learning. We now know what are the building blocks of deep learning. That is a perceptron. So what is an activation function? How we can plug in put all these building blocks and build the neural networks. In the next video, we will see about what is backpropagation. Thank you.